All right, 17.3 is acid-base titrations. This is strong acid, strong base. This is a very, very, very long, complicated thing. So grab yourself a calculator, grab yourself some paper, let's go. So we're going to be graphing some titrations, and we've done this before in terms of doing titrations, but we've never graphed it. And so as a titration proceeds along, the big thing that you need to know is what's happening as far as pH. And so in this particular reaction, we're starting with HCl. And what we're adding to it is NaOH. And so you've got this reaction, HCl plus NaOH. And that's going to make NaCl and H2O as your final product. And so what's happening to this HCl? You know, if we have two H's here, now we have one H, and now we have no H's. The H, as we go this way, the H disappears. Okay? Because that's being neutralized by the OH negative. But you notice we don't have any OH negative here, we don't have any OH negative here, and we don't have any OH negative here. And that's because we're not seeing what's really happening. What's really happening is the H plus and the OH negative together are making water. And so one of these H pluses disappeared because it added with the OH negative to make water. Until we reach a certain point, so we've got acidic, 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 all of a sudden it switches to being basic. And that's the point at which this OH negative starts to show up as like an excess because I've officially run out of H. And where you're going to see that OH show up is after this point called the equivalence point. And the thing about the equivalence point is we're going to use this equation, MaVa equals MbVb, in order to find that. Because the thing we know about the equivalence point is that at the equivalence point, moles of acid are equal to moles of base. And we did this last year. So moles of acid is molarity of acid times volume of acid, because remember, molarity of acid is moles over liters times liters. And so your liters cancels out, and you get, hey, look, moles of acid equals moles of base. And so that's what we're going to do with this. We're going to do all the math. So these are the equations that we're going to do, or all the points that we're going to do. And we're actually going to go from top to bottom. And it seems a little backwards and kind of scattered, but it actually does make sense. The big thing is try to space your points out evenly. So if I was looking at this graph, the points that I would want to do are X, so 0. I would want to do 50, because that's where your milliliters of NaOH. I'd want to do halfway, so 25. And then I'd want to find two spaces, so like maybe 10 and 40, sort of your in-betweens. And then probably like that guy, which is about 60. So in terms of milliliters of NaOH, those are the ones that I'd probably want to do. And like somewhere along those lines. I like picking nice even numbers just to make it a little bit easier. So that's what we're going to do right now. We're going to space those out. And so, for starters, your initial point is misleading a lot of times. People think that the initial point is harder than it is. This is all I care about, because the initial point is just based on what the acid is. It actually doesn't even matter what your volume is, and it definitely doesn't matter what your NaOH is. So for this particular titration, remember pH is the negative log of the concentration of H+. And so in this case, the negative log of 0.40 would be your pH. And hey, look, that is actually 0.40. So there's your first point. So your first point is an X of 0 milliliters of NaOH added, and a pH of 0.40. Because what we're trying to do is we're trying to generate this graph. My X is milliliters of NaOH, my Y is pH. All right? All right, point 2 is your equivalence point. So the way the equivalence point works is you're going to be rocking the molarity. So Ma times Va equals Mb times Vb. You're going to be using that equation. And so really what we're saying is moles of acid equals moles of base at the equivalence point. So my molarity of my acid is 0.40, and that's being multiplied by 90 milliliters. And that's going to be equal to molarity of base, so 0.1. And that's going to be multiplied by my volume of base. And so if I do that math, 90 times 0.4 divided by 0.1, I get 360 milliliters, and that's equal to the volume of base. And so my equivalence point occurs at some number 360, comma, whatever my pH is. And so here's the kind of silly thing that people often forget. The pH here is 7. And I know the pH here is 7 because we're talking about a strong acid and a strong base. And anytime you're talking about a strong acid and a strong base, the pH is always 7. And there's a logical explanation. If you do HCl and NaOH, your leftover is salt water, NaCl and H2O. So we said this was a strong acid, so its conjugate has negligible basic character. And we said this is a strong base, so its conjugate has negligible acidic character, and so together they're neutral, and so this solution has a pH of 7. So that is point number 2 for our graph, 360, 7. All right, we're going to go halfway in between now. And so this is the halfway point. And the way the halfway point works is we're going to start to get into some neutralization stuff. And so I want to go ahead and write HCl and NaOH. That's my equation. And I'm going to put that together and make NaCl and H2O. And we're going to work this out using what's called a BA table. BA just stands for before and after. And I like this because it allows us to see the stoichiometry really easily. And so we're going to start with 90 milliliters times 0.4 molar. So let me add in a little milliliter. So milliliter times molar, 90 times 0.4 is 36. And that's milliliters times moles. So that's actually millimoles. Not moles, but millimoles. And then this is my halfway point. So the question is, what's the volume at the halfway point? Well, we said the equivalence point was 360 milliliters. So the halfway point is 180 milliliters. And so we're going to do 180 milliliters. And we're going to multiply that by 0.1. And so now we've got 180 times 0.1, which is 18. Hey, look, it's half of 36. No way. The halfway point. Who'd have thunk? And so what's going to happen when I mix these two things together? 36 and 18, half of this is going to disappear. So I'm going to subtract 18 from this and subtract 18 from this. And I have 18 millimoles left over. And here I have nada, niente, nothing. Okay. On the other side, NaCl, I started with nothing, and now I have 18. Because remember, whatever was disappeared here is up here, and this I really don't care about, so I'm going to ignore him. All right. Okay. Almost there. The last thing is we need to find pH. So pH equals the negative log of the concentration of H+. And so my H+ is coming straight from my HCl. And so all I have to do is find that concentration. And so what I know about concentration is that it's moles per liter. So what I have is 18 millimoles. And then I have a solution that is changing. It's going to consistently change. So I started with 90 milliliters. And I added to it 180 milliliters, and those two things dilute each other. And so my new volume is 90 plus 180. I need to include both of those. And so the log of that will end up being my pH. And so for the halfway point, I got a pH of 1.18. Okay, new point. 180 milliliters, pH of 1.18. So that's 0.3 that I have so far. All right. Okay, next point is our in-betweens. And so your in-betweens, I've noticed that there's kind of a 90 thing going on, so I'm just going to keep going with that. And so HCl and NaOH, same old, makes NaCl and H2O. And so I'm going to start here with my before. My before was 36 millimoles last time. That's not going to change, so I'm just going to keep going with that. And then my NaOH, we're going to do an in-between, so let's go ahead and do 90. So we'll do 90 milliliters there. And so if you're looking at 90 milliliters, that's going to be, it's going to be 90 milliliters times 0.1, and so that's 9 millimoles. Okay, after 36 minus 9 is going to be 27, and this guy is 9 minus 9, aka 0. And then this guy will be 9. Because if 9 disappeared from this side, 9 appeared on this side. So 0, and then don't care. And so for this one, my pH is my negative log of H+. And H+, again, is equal to your HCl because it's a strong acid. So negative log of 27 millimoles divided by what we started with, 90, plus what we added, 90. So 90 plus 90, aka 180. And so pH for that point, I got to be 0.82. So that's my next point. I have 90, 0.82. And then the next thing I want to do is another in-between. So I'm going to do HCl and NaOH again. And this in-between we're going to do is on the other side of the halfway point. And so if we just did 90, and then we've already done 180, let's go ahead and do 270 milliliters. And so for this guy, 36 millimoles was my before. And so this guy is 270 times 0.1. milliliters, sorry, and 0.1 molar. So that's 27 millimoles. So we have 36, we're adding 27. After we will have 9 left over, and then here we'll have nothing. Because again, 27 minus 27 is 0, 36 minus 27 is 9. Over here we are adding 27. So if we're subtracting 27 millimoles on this side, we have to be adding 27 millimoles on this side. And again, still don't care about water. And so pH on this side is the negative log of H+, which in this case is 9 millimoles. And then divided by our total volume. Our total volume is the 90 we started with, plus the 270 we just added. So 90 plus 270. And so pH of that guy is 1.60. So there's another new point, 270 milliliters with a pH of 1.60. Okay, almost there. So the last point is after the equivalence point. After the equivalence point, this is the point at which you're going to exceed your capacity. So HCl plus NaOH makes NaCl and H2O. These are all the same neutralization question. Starting with 36 millimoles, what we've started with for the last couple, and then we're going to do after. And so we've done 90, 180, 270, 360. So let's go ahead and hit 450 just to keep that 90 rolling. And so this is going to be 450 times 0.1, so milliliters, times 0.1 molar, and we have 45 millimoles. So for the first time, our limiting reactant has switched. So because 36 is less than 45, this is now my limiting reactant. So 36 minus 36 is 0. And 45 minus 36 is 9. So I actually have left over NaOH instead of HCl this time, which should tell me that this solution is going to be basic. 36 minus 36 is 0, so I'm losing 36 on the left, which means I'm adding 36 on the right. And this guy's 0, so ignore him. And so for this guy, I cannot find pH. I'm going to have to switch it up. I'm going to find POH, because in this case, I've got OH negative, not H+. And so POH is equal to the negative log of 9 millimoles. And that 9 millimoles is in a solution that contains 450 milliliters of NaOH and 90 milliliters of HCl. So again, those things still count. They're still diluting each other. Okay. And so for POH, I got 1.78, which means pH equals 14 minus POH. So 14 minus 1.78, and that brings us to 12.22. And again, that solution is basic, so that is what we're looking for. And that point is 450, comma, 12.22. Okay, last point in that. And so now your last step is to graph this guy. And so when I graph each of those points, it kind of looks like that. And so these points together look like they would be a nice, cute little curve, but they're actually not. You need to pay attention to this sort of line. So see how we have this little sort of S shape, like very, very, very like faint, and then all of a sudden a quick change. And so we need to make sure that we're replicating that. We're not including all the points that we would need to be able to get that sort of detail. So we're just going to kind of have to fake it. So we're going to do this, and then notice I'm going to keep that curve going until I hit that very steep section. And this is where it gets a little tricky. And then something like that. Whoops, kind of missed that point, but you get the gist. So something along those lines. Again, acidic, and then all of a sudden it flips to being basic. And I want you to notice my equivalence point right there at 7.0, right smack dab in the middle. All right, so question is, how do you do this in real life? And we've done this in the lab before, where we added an indicator. And so the indicator that we used last year was phenolphthalein. And the reason we used phenolphthalein because we were doing a strong acid, strong base titration. And phenolphthalein changes at around a pH of 8. And so if you're looking at this equation, this guy has an equivalence point of around 9. And so phenolphthalein was chosen because it changes color right at the equivalence point. But in this guy, this is methyl red, and methyl red changes color right down here. And so this is actually a really terrible choice of indicator for this reaction because my equivalence point is right here at about 9, and methyl red changes way too early. And so this is kind of like the type of question would be something like, what would be the best indicator for this? And so your job is to find the equivalence point, pH, and then figure out how that compares to the color change. Okay? Big section, big chapter. Lots and lots and lots of stuff going on with the strong acid, strong base. This is the basis for your titration project, so make sure that you understand this. I know this has been a long one, but trust me, it's worth it. So if you have any questions, write them down. We'll do a lot of these as practice.